What if everything you've ever known, every sunrise, every heartbeat, every moment of human history was just a fleeting flicker in the grand cosmic clock? What if time itself, the invisible force that shapes our existence, isn't infinite but has an expiration date? Picture the universe as we know it, not just fading into darkness, but vanishing in ways so bizarre and unimaginable that even the brightest minds struggle to comprehend them. This isn't science fiction. It's a question scientists and philosophers have wrestled with for centuries. How will time itself meet its end? The idea of time's demise isn't just about clocks stopping or calendars running out. It's about the very fabric of reality unraveling, about forces so vast and mysterious that they defy our everyday understanding. Some theories suggest a slow, cold fade into nothingness. Others predict violent, cataclysmic finales where the laws of physics themselves break down. And then there are the possibilities so strange they sound like something from a dream: time loops, alternate dimensions, and cosmic resets that could rewrite existence as we know it. In this journey, we'll explore 30 of the most mind-bending theories about how time could end. From the heat death of the universe to the eerie possibility of a big crunch, from black holes swallowing reality to quantum anomalies that could erase time altogether, each theory is a window into the profound and often unsettling mysteries of our cosmos. This isn't just about doom and gloom, it's about wonder, about the breathtaking scale of the universe and our place within it. So buckle up. By the time we're done, you'll never look at a ticking clock the same way again. The first stop on our journey through time's possible endings is a cosmic mirror image of the universe's birth, the Big Crunch. Imagine the expansion of the universe, that relentless outward rush of galaxies we've observed for decades, suddenly slamming into reverse. Instead of spreading endlessly into the void, everything, every star, every planet, every speck of dust gets pulled back by gravity's unyielding grip. This isn't just a slowdown, it's a full-scale collapse, a grand rewinding of creation itself. Scientists call this the Big Crunch, and it starts with a simple but staggering idea. What if there's just too much stuff in the universe? Gravity, the force that keeps your feet on the ground and planets in orbit, might one day overpower the expansion fueled by dark energy. Galaxies would begin drifting closer, then hurtling toward one another. Space itself would shrink, temperatures skyrocketing as cosmic distances collapse. Eventually, all matter, every atom, would be crushed into an infinitely dense point, a singularity eerily similar to the one that birthed our universe in the Big Bang. But here's where it gets even stranger. In this scenario, time itself wouldn't just stop. It could become meaningless. At the moment of the crunch, the laws of physics as we know them would break down. There'd be no before or after, no cause and effect, just an unfathomable state where even the concept of time ceases to exist. Some theorists speculate this might not be the end at all, but a reset button for reality, with the singularity birthing a brand new universe in an endless cycle. Yet the Big Crunch isn't inevitable. For it to happen, the universe would need enough matter to overcome dark energy's push, and right now, the evidence suggests expansion is accelerating, not slowing. But that doesn't rule it out entirely. If dark energy weakens over time, or if we've misjudged the density of the cosmos, gravity could still have the final say. It's a reminder that even the mightiest forces in existence are locked in a silent tug of war, one that could decide the ultimate fate of time itself. What makes the Big Crunch more than just a dramatic cosmic finale? The answer lies in the delicate balance between two invisible forces: dark matter's relentless pull and dark energy's mysterious push. For decades, astronomers have measured galaxies racing away from each other, evidence of an expanding universe, but hidden within that motion is a subtle tug of war. Dark matter, that unseen gravitational glue holding galaxies together, could, if dense enough, gradually slow and reverse the expansion. Picture a ball thrown upward, but instead of coasting into space, it pauses at its peak and plummets back to Earth. That's the essence of the Big Crunch scenario, yet there's a twist: dark energy. Discovered in the late 1990s, this enigmatic force behaves like anti-gravity, accelerating the universe's expansion. Imagine inflating a balloon, but instead of slowing down, it starts inflating faster over time. Current observations suggest dark energy is winning, making the Big Crunch seem unlikely. But science is full of surprises. Some models propose dark energy might weaken over billions of years, or even flip its properties entirely, switching from repulsion to attraction. If that happens, the stage could still be set for a collapse. Then there's the quantum wildcard: tiny fluctuations in the fabric of spacetime that, under extreme conditions, could destabilize the universe's expansion. Think of it like a bridge vibrating in the wind. At a certain frequency, those vibrations could grow uncontrollably, triggering a collapse. Certain string theory models even suggest hidden dimensions might leak gravitational energy, subtly shifting the balance between expansion and contraction over eons. The debate isn't settled. While most data points to an ever-expanding cosmos, some anomalies linger. For instance, discrepancies in measurements of the Hubble constant, the rate of the universe's expansion, hint at gaps in our understanding. Could there be unknown forces or matter types tipping the scales? The Big Crunch remains a tantalizing what if, a reminder that the universe's fate hinges on forces we're still struggling to measure. Whether it's a future collapse or an endless drift into cold darkness, one thing's certain: time's ultimate destiny is far stranger than we can imagine. The universe doesn't always end with a bang. Sometimes it fades away in silence. Picture a cosmic graveyard where every star has burned out, every black hole has evaporated, and the vast expanse of space is nothing but a freezing, featureless void. This is the heat death, a fate more chilling than any explosion, where time doesn't so much stop as become irrelevant. At the heart of this theory lies entropy, the universe's slow march toward disorder. Think of it like a cup of coffee left on the counter. It starts hot, but over time, heat spreads out until it matches the room's temperature. No more warmth to extract, no energy left to use. Now scale that up to cosmic proportions. Stars convert fuel into light and heat, but eventually they'll exhaust every last drop. Galaxies will dim, and space itself will stretch so thin that even the closest particles are light years apart, unable to interact. The universe reaches maximum entropy, a state where nothing happens because everything is evenly distributed. No more energy gradients, no more change, just eternal, icy stillness. But the heat death isn't just about cold and darkness, it's about the disintegration of matter itself. Protons, the building blocks of atoms, might not last forever. Some particle physics models suggest they could decay over unimaginable timescales, trillions upon trillions of years, breaking down into lighter particles, until even the remnants of planets and stars dissolve into faint whispers of radiation. Black holes, those cosmic vacuum cleaners, aren't safe either. Thanks to Hawking radiation, they slowly leak energy, shrinking over eons until they vanish in a final, quiet puff. Yet even in this desolate scenario, there's a glimmer of strangeness. Quantum mechanics hints at bizarre possibilities, like vacuum fluctuations, tiny bursts of energy that could, given enough time, spontaneously spawn new particles or even entire universes. It's called quantum resurrection, a speculative idea that in a universe dead for eternity, random quantum events might eventually kickstart reality all over again. Of course, we're talking timescales so vast they make the age of our current universe look like a blink. The heat death isn't just one possible ending, it's currently the most likely based on our understanding of thermodynamics and cosmic expansion. With dark energy accelerating the universe's dispersal, gravity may never get the chance to pull everything back in a big crunch. Instead, we could be heading toward the ultimate equilibrium, a state where time loses all meaning because nothing left can change. No clocks tick, no minds ponder, just an endless, uniform sea of near absolute zero. Still, the universe has a way of surprising us. Maybe dark energy's behavior will shift, or undiscovered physics could rewrite the rules. For now, the heat death stands as a haunting reminder that even the cosmos isn't immune to decay, and that the most profound endings aren't marked by fury but by silence. If you think 1 billion years is a long time, brace yourself. The heat death unfolds on timelines so vast they defy human comprehension. We're talking 10 to the power of 100 years or more, numbers so large they have more zeros than atoms in the observable universe. To put that into perspective, if you wrote out the number in full, it would stretch across galaxies. This isn't just the distant future, it's a timescale where the universe becomes unrecognizable, a place where even the mightiest structures, black holes, neutron stars, the last remnants of galaxies, will have long since vanished. During this unfathomable era, space itself becomes a graveyard of exhausted energy. Stars, those brilliant beacons of light, will have burned out trillions of years earlier. Galaxies, now dark and scattered, drift so far apart that their light can no longer reach one another. The universe expands into an infinite freezer, its temperature creeping closer and closer to absolute zero. But then comes an eerie twist. Quantum mechanics doesn't take a vacation, even in this frozen wasteland. Tiny fluctuations in the vacuum of space could, statistically, give rise to something called a Boltzmann brain. Imagine a self-aware consciousness spontaneously forming from random particle collisions, existing for just a fleeting moment before dissolving back into the void. These hypothetical entities wouldn't have bodies or planets to stand on. They'd be lonely flashes of thought in an otherwise lifeless cosmos, questioning their own existence before vanishing without a trace. Yet even this bleak timeline might not be the final word. Some theories suggest the vacuum of space isn't as stable as it seems. What if, buried in the fabric of reality, there's a lower energy state lurking like a hidden trapdoor? If triggered by a quantum fluctuation or some unseen force, the universe could undergo vacuum decay. A bubble of true vacuum would form, expanding at the speed of light, rewriting the laws of physics as it goes. One instant, the cosmos is cold but stable. The next, it's erased without warning, replaced by a new reality with entirely different rules. Contrast this with shorter-term cosmic events, supernovas, black hole mergers, even the death of our own sun, which seem dramatic but are mere blips on the universal calendar. In the face of heat death, these fiery spectacles are like sparks from a campfire, bright but brief, while the true fate of time stretches into an abyss of quiet dissolution. Whether through Boltzmann brains, vacuum decay, or sheer endless cold, one thing is certain. The universe's final act won't be a dramatic collapse or a fiery rebirth, but a slow, inevitable fade into the deepest silence imaginable. The cosmos might not fade quietly into the cold. It could be torn apart in a final, violent crescendo. Enter the Big Rip, a fate so extreme it makes black holes look tame. Picture dark energy, that mysterious force accelerating the universe's expansion, growing stronger over time until it overpowers gravity, electromagnetism, even the nuclear forces holding atoms together. This isn't just about galaxies drifting apart. It's about reality itself unraveling at the seams. The key lies in a hypothetical form of dark energy called phantom energy, which doesn't just push space outward, it intensifies as the universe expands. Think of it like a car's accelerator pedal stuck to the floor with the speed increasing endlessly. If phantom energy exists within a finite window, perhaps 60 billion years from now, its grip would become unstoppable. First, galaxy clusters would be ripped apart, their gravitational bonds shattered. Next, individual galaxies would disintegrate as stars are flung into the void. Then the horror reaches our doorstep, solar systems torn asunder, planets ripped from their orbits, but the true nightmare comes in the final minutes. As phantom energy's density crosses a critical threshold, space-time itself becomes a casualty. Stars explode as the forces binding them collapse. Then, mere instants before the end, atoms, the very building blocks of matter, are shredded apart. Protons and electrons can no longer cling together. Even atomic nuclei disintegrate. Space stretches so violently that time, matter, and the fabric of reality cease to function. The universe doesn't just end, it's erased in a single, incomprehensible moment. Yet there's a haunting twist. Some models suggest the Big Rip wouldn't leave total nothingness. Instead, space-time might fracture into isolated patches, each a disconnected bubble floating in an abyss, their physics forever severed from one another. It's a chilling thought. No shared future, no shared past, just fragments of what once was, drifting alone in the dark. The Big Rip hinges on dark energy's still unknown nature. Current observations show the universe's expansion accelerating, but whether dark energy strengthens enough to trigger a rip remains unclear. If it does, the countdown isn't just to the end of time, it's to the dissolution of reality's very rules. One thing's certain: if phantom energy is real, the cosmos won't go gently into that good night. It'll be screaming. Among all the theories about time's end, few are as abrupt or as terrifying as the vacuum metastability event. Imagine the universe as a precarious balancing act teetering on the edge of a cosmic cliff. Right now, we exist in what physicists call a false vacuum, a seemingly stable state that's actually a temporary illusion, like a marble resting in a shallow dent on a hillside. But if something nudges that marble over the edge, the entire hillside could collapse, and with it, reality as we know it. At the heart of this scenario lies the Higgs field, an invisible energy field that gives particles their mass. For decades, scientists assumed it was stable, but recent calculations suggest it might not be. The field could be in a metastable state, seemingly solid but capable of suddenly shifting into a lower energy, true vacuum. If that happens, a tiny bubble of this true vacuum could form somewhere in the universe, perhaps due to a random quantum fluctuation. Once triggered, this bubble would expand outward at the speed of light, rewriting the laws of physics as it goes. Here's the chilling part: you wouldn't see it coming. The change would propagate faster than any signal or warning could travel. One moment, the universe operates under familiar rules. The next, the bubble's boundary sweeps through Earth, instantly altering fundamental forces like electromagnetism and gravity. Atoms might fly apart, molecules dissolve, or matter itself cease to exist in any recognizable form. Even causality, the relationship between cause and effect, would be erased, as the new physics wouldn't necessarily support the same logic that governs our reality. This isn't just wild speculation. The Higgs field's potential instability was first hinted at by calculations involving its measured mass and interactions. If the field's energy isn't at its absolute lowest state, like a stretched spring still holding tension, then a sudden drop could be catastrophic. Some models even suggest that high-energy events, like particle collisions in extreme cosmic environments, could trigger the transition prematurely. Yet there's a strange paradox here. The universe has lasted nearly 14 billion years without collapsing into a true vacuum. Does that mean we're safe? Not necessarily. Vacuum decay could be statistically inevitable over vast timescales, a ticking time bomb hidden in the fabric of space-time. And unlike other cosmic doomsday scenarios, this one wouldn't leave any aftermath to study. Just an entirely new universe playing by different rules with no trace of what came before. The unsettling truth: we might already be in the danger zone. Experiments at particle colliders like the Large Hadron Collider briefly create conditions of extreme energy, leading some to wonder, could we accidentally poke the universe too hard, nudging that marble over the edge? Most physicists dismiss this as improbable, but the fact that it's even a topic of debate underscores how little we truly understand about the stability of reality. If there's any comfort to be found, it's this: if vacuum decay happens, it'll be over too quickly to comprehend. No panic, no slow descent into chaos, just an instantaneous reset button for existence itself. The universe wouldn't end with a whimper or a bang, but with a silent, unstoppable rewrite of its own code. And in that final moment, time wouldn't just stop, it would be rendered meaningless, a forgotten rule in a game that no longer exists. What if the end of time isn't really an ending at all, but just the start of another cosmic chapter? That's the mind-bending premise of the cyclic universe theory, a universe that doesn't die but reinvents itself in an endless loop of big bangs and big crunches. Picture a cosmic heartbeat, expanding and contracting over unimaginable eons, each cycle birthing a new reality from the ashes of the old. At the forefront of this idea is Nobel Prize-winning physicist Roger Penrose and his conformal cyclic cosmology. He proposes that when the universe reaches its maximum expansion, stretched so thin that all matter dissolves into radiation, time itself loses meaning. In this state, the distinction between past and future evaporates, allowing the universe to reset into a new Big Bang. But here's the twist: Penrose believes traces of the previous cycle might linger. He claims to have found faint, circular patterns in the cosmic microwave background, ghostly imprints of supermassive black holes from a universe that existed before ours. If true, these Hawking points could be cosmic fossils, evidence that time's arrow isn't straight but cyclical. String theory offers another take on the cycle, with a vision straight out of science fiction. Imagine our universe as a three-dimensional brane floating in a higher dimensional space, like a sheet of paper suspended in a vast room. Other branes might drift nearby, and when they collide, boom, a new Big Bang ignites. These collisions wouldn't just be random crashes. They could be finely tuned events, with each collision setting the precise conditions needed for galaxies, stars, and life to emerge again. Some models even suggest that the dark energy accelerating our universe's expansion is a precursor to the next collision, a cosmic countdown to rebirth. But how could anything survive these apocalyptic resets? The answer might lie in quantum information. In some cyclic models, the universe's fundamental information, the quantum states of particles, isn't destroyed but recycled. Think of it like shredding a document and then reassembling it perfectly from the fragments. Black holes could play a key role here, their event horizons preserving information like cosmic hard drives, only to release it in the next cycle. Even consciousness, some speculate, might find a way to persist, encoded in the very fabric of space-time. Critics argue that cyclic models stretch the limits of known physics. Entropy, the measure of disorder, should increase with each cycle, making successive universes more chaotic. How could complex structures like galaxies form again if everything is increasingly disordered? Penrose counters that in the conformal reset, entropy is effectively erased, like hitting a cosmic refresh button. Others point out that brane collisions would likely be too violent to produce the orderly universe we see, unless some unknown force fine-tunes each collision with eerie precision. Yet the allure of a cyclic universe endures. It offers a poetic alternative to the cold finality of heat death or the nihilism of the Big Rip. Time becomes not a straight road to oblivion but a vast cosmic circle where endings are beginnings and nothing is ever truly lost. Whether through Penrose's conformal echoes, colliding branes, or some deeper mechanism we've yet to discover, the idea invites us to see the universe not as a one-time event, but as an eternal story, rewritten again and again across infinity. What if the three-dimensional world we experience, every mountain, ocean, and star, is nothing more than an illusion, a cosmic projection like a hologram cast from the edge of reality itself? This is the essence of the holographic principle, one of the most radical ideas in modern physics. It suggests that all the information in our universe, every particle, every force, even time, might be encoded on a distant two-dimensional surface, like a movie playing on the surface of a bubble. But what happens when the projector fails? The roots of this theory stretch back to the black hole information paradox. When matter falls into a black hole, it seemingly vanishes, violating a fundamental rule of quantum mechanics. Information can never be destroyed. Yet black holes evaporate over time, leaving no trace of what they consumed. To resolve this, physicist Gerard T. Hooft proposed that all the information swallowed by a black hole isn't lost but smeared across its event horizon, the point of no return. Think of it like a cosmic hard drive where three-dimensional data gets compressed into a two-dimensional surface. This led to a staggering realization. If black holes can encode 3D information in 2D, maybe the entire universe does the same. Enter the AD/S/CFT correspondence, a mathematical framework that solidifies this idea. It posits a perfect duality. A higher dimensional universe with gravity, like ours, can be perfectly described by a lower dimensional system without gravity, like a sheet of quantum code. Picture a video game where every character, landscape, and physics interaction is actually just lines of programming on a flat disk. If that's true for our universe, then time itself might be an emergent property, a side effect of this holographic projection. But here's where things get eerie. If the underlying code, the two-dimensional boundary, becomes corrupted or degrades, the hologram could glitch or collapse. Imagine a DVD scratched just enough to freeze the movie or distort the images. In cosmic terms, this might mean sudden paradoxes, time loops where cause and effect break down, regions of space where gravity fluctuates wildly, or even patches of reality where time simply stops. Some models suggest that quantum errors in the boundary's information could manifest as dark energy, accelerating the universe's expansion, or worse, triggering a tear in the holographic fabric itself. The most unsettling implication, we might never see it coming. A holographic breakdown wouldn't follow the laws of physics as we know them, because those laws are part of the projection. It'd be like a character in a game realizing their world is pixelating, except the rules preventing that realization are crumbling too. Could strange anomalies in deep space, like unexplained voids or regions where time seems to move differently, be early signs of such corruption? While the holographic principle remains speculative, it forces us to confront a profound possibility. Time isn't a fundamental feature of the universe but a fragile illusion, dependent on a deeper layer of reality we can't yet perceive. And if that layer ever falters, the clock might not just stop, it could vanish entirely, leaving no trace that it ever existed at all. What if everything around us, the stars, the oceans, even the passage of time, isn't real, but lines of code in an unfathomably advanced simulation? This is the heart of the simulation hypothesis, a theory that's gained traction among philosophers and tech luminaries like Elon Musk. And if we are living in a simulated reality, there's a chilling possibility. The beings running it could pull the plug at any moment. Unlike cosmic disasters or entropy, this wouldn't be an end dictated by physics. It'd be a deliberate shutdown, like closing a laptop mid-game. Philosopher Nick Bostrom framed this scenario as part of his famous trilemma. He argued that at least one of these statements must be true. 1. Almost all civilizations at our level go extinct before becoming technologically advanced. 2. Advanced civilizations lose interest in creating ancestor simulations. Or 3. We're almost certainly living in a simulation right now. The math behind it is sobering. If even a single advanced civilization survives long enough to run ancestor simulations, and they have the computational power to create countless virtual worlds, the odds tilt overwhelmingly toward us being in one of those simulations rather than the original reality. But what would a simulation shutdown look like? It might not be dramatic. The creators could simply halt the program, freezing every atom in place, time stopping mid-tick. Or they might initiate a systematic collapse, stars winking out, laws of physics glitching, or reality fragmenting into digital noise. Some theorists speculate we've already seen hints of this. Unexplained quantum anomalies, like particles behaving differently when observed, could be artifacts of rendering limits, the universe's version of a lagging video game. Even déjà vu, those eerie moments of false familiarity, might be bugs in the code, brief lapses where the simulation stutters. Then there's the energy problem. Running a universe-sized simulation would require unfathomable computational resources. What if the creators face their own limits, a power shortage, hardware failure, or even a decision to repurpose their systems? Think of it like deleting old files to free up space. Our entire history, from the Big Bang to this very moment, could be erased not out of malice but indifference. But here's the twist: a shutdown might not mean oblivion. In some models, simulated universes aren't terminated but archived, saved in some cosmic database, perhaps to be rebooted later. Others suggest that conscious beings within the simulation could be migrated to another instance, like characters transferred between servers in an MMO. It's a strange comfort, the idea that our end might just be a pause button pressed by entities we'll never comprehend. The simulation hypothesis forces us to confront an unnerving question. If reality is artificial, then time itself is just another variable in the code, as editable as the settings in a video game. And when the programmers decide they're done, time won't just end, it'll be deleted. Imagine a version of you that never dies, not because of biological immortality, but because your consciousness keeps slipping into timelines where you survive. This is the spine-tingling premise of the quantum immortality paradox, a thought experiment that twists quantum mechanics into something straight out of a Twilight Zone episode. At its core lies the many worlds interpretation, the idea that every quantum decision spawns alternate realities. But here's the unsettling twist: from your subjective perspective, you might only experience the branches where you're still alive, creating an illusion of invincibility. Think back to Schrödinger's famous cat, both dead and alive in its box until someone looks. The moment you open the box, the universe chooses a state. But many worlds suggests there's no choice at all. Instead, reality splits, one world where the cat purrs, another where it lies stiff. Now replace the cat with you. In any life-threatening scenario, a car crash, a fall from a height, quantum randomness could produce timelines where you miraculously survive. From your viewpoint, you'd only remember the timeline where the airbag deployed, the rope held, the bullet missed. Over countless near-death moments, your consciousness would seem to dodge death indefinitely, like a ghost stepping between raindrops, but there's a dark flip side. If this were true, you'd eventually find yourself in increasingly improbable situations, the sole survivor of a plane crash, a pandemic, even Earth's destruction. The laws of probability would stretch to absurdity as you're funneled into rarer and rarer branches where existence persists. Picture an old version of yourself, centuries from now, floating in the ruins of a dead universe, kept alive by quantum fluctuations just barely sustaining your brain activity. At some point, subjective time might become unbearable, an endless, lonely crawl through a collapsing cosmos where death isn't an end, but a door you're never allowed to open. Critics argue this relies on a skewed definition of consciousness. If identity is tied to the physical brain, how could it jump between branches? Others counter that it's not about jumping. It's about the illusion of continuity created by only experiencing surviving versions. There's also the measurement problem. Why does observation seem to force reality into one state for the observer? Quantum immortality turns this into a macabre game of chance where the observer's survival biases their perception of outcomes. While mainstream physics dismisses this as speculative, the paradox forces us to confront deep questions about awareness and reality. If consciousness is just a series of survived moments, does that make death a statistical illusion? Could there be versions of us in other branches who experienced our deaths while we blithely continue? It's a theory that blurs the line between physics and philosophy, leaving us wondering whether time's end is an absolute horizon, or just the one we're fated to never see. In the unfathomable stretches of a heat-death era universe, as matter thins into near nothingness and the cosmos approaches absolute zero, something bizarre might emerge from the void, not by design but by sheer random chance. Welcome to the Boltzmann brain paradox, a thought experiment that turns our understanding of consciousness and reality inside out. The premise is deceptively simple. Given enough time, even the most improbable events become inevitable. In a lifeless, nearly empty universe, quantum fluctuations could spontaneously assemble atoms into a fully functioning, self-aware brain complete with false memories of a past that never existed. This isn't science fiction. It's a consequence of statistical mechanics born from Ludwig Boltzmann's work on entropy in the 19th century. If you wait long enough, say 10 to the power of 10 to the power of 50 years, random particle collisions could form any configuration of matter, no matter how unlikely. Picture a tornado assembling a 747 from scrap metal, but scaled up to cosmic absurdity. A Boltzmann brain wouldn't need a body or a world to inhabit. It would flicker into existence for a split second, convinced it was a human named John living in 21st century Chicago, only to dissolve back into the void moments later, its entire life a fleeting statistical hiccup. But here's where it gets unsettling. If Boltzmann brains are possible in the far future, could we be them right now? The odds of our universe being real versus a random fluctuation seem better until you consider the timescales involved. Over infinite time, Boltzmann brains should vastly outnumber real observers like us. Statistically, it's more likely you're a momentary accident of quantum noise than a product of 14 billion years of cosmic evolution. This idea horrifies physicists because it renders all empirical knowledge suspect. Your memories, the laws of physics, even the sensation of reading these words, all could be a phantom dance of particles with no connection to an external reality. This paradox ties directly to time's arrow, the one-way flow from order to disorder. Normally, entropy increases over time, making complex structures like brains the product of low-entropy beginnings like the Big Bang. But in a universe that lasts forever, entropy can sometimes locally decrease, creating order from chaos. The disturbing implication, time's arrow might not point the way we think. Instead of being early observers in a young universe, we could be freak fluctuations in an ancient, dead one. Our perception of cosmic history just an elaborate illusion. Not everyone finds this plausible. Critics point out that Boltzmann brains require a static universe, whereas ours is expanding exponentially due to dark energy. In such a cosmos, space stretches too quickly for particles to regroup into complex structures, making spontaneous brain formation practically impossible. Others argue that even if Boltzmann brains dominate in the far future, our current low-entropy state makes real observation far more likely for now. Some theories, like the holographic principle or multiverse models, offer escape routes by altering how probabilities are calculated across realities. Yet the paradox lingers because it exposes how little we truly grasp about consciousness and reality's foundations. Are we the rule or the ultimate cosmic glitch? The Boltzmann brain scenario doesn't just challenge our place in time. It threatens to reduce all existence to a hall of mirrors where every thought, every moment might be nothing more than entropy's fleeting dream. What if time isn't a one-way street but a winding road that could suddenly reverse direction? The idea isn't just science fiction. It's rooted in a fundamental symmetry of physics called CPT symmetry, which suggests that the universe might look identical if you flip charge, parity, and time all at once. This opens the door to a staggering possibility. Entropy, the force that drives time's arrow forward, could spontaneously decrease, causing the universe to rewind like a film in reverse. Picture the aftermath of a shattered wine glass suddenly reassembling itself, shards leaping back into place as spilled liquid retreats into the vessel. That's the essence of time reversal on a cosmic scale. According to CPT symmetry, every particle interaction should work the same way backward as forward electrons zipping backward in time are mathematically identical to positrons moving forward. Some theorists argue that if entropy could locally decrease, even briefly, events might unfold in reverse sequence without violating physical laws. Retrocausality experiments add fuel to this fire. In quantum mechanics, particles seem to decide their properties retroactively based on future measurements, as if time's boundaries are blurred. Take the delayed choice quantum eraser experiment, where a photon's behavior appears to change based on decisions made after it's already been detected. It's as if the future is whispering back to the past, tweaking reality in real time. If this effect scales up, could the universe itself someday flip its temporal script? But a universal rewind wouldn't just mean watching history play backward, it would erase the future entirely. Every invention, every birth, even the memory of those events would unravel, leaving no trace they'd ever existed. The cosmic clock would tick backward toward the Big Bang with one chilling twist. Observers inside the reversal wouldn't perceive it as backward at all. To them, entropy's decrease would feel just as natural as its increase does to us, their past becoming our future. Critics counter that while CPD symmetry holds at the quantum level, macroscopic entropy is overwhelmingly likely to increase. The odds of all particles in a system spontaneously reversing course are astronomically low, like shuffling a deck of cards into perfect order by chance. Yet in an infinite or cyclic universe, even the rarest events might eventually occur. Some models propose that a big bounce could reset entropy at each cycle, while others suggest quantum gravity effects near the universe's death could trigger a reversal. Time's reversal isn't just a thought experiment, it's a lens on reality's deepest mysteries. If the universe can rewind, then the future isn't just uncertain, it's perpetually at risk of being undone. A sandcastle waiting for the tide of entropy to drag it back into the sea of possibilities. Long after the last stars flicker out and galaxies dissolve into darkness, one celestial force will still reign supreme: black holes. These cosmic titans, born from the collapse of massive stars, will outlast everything else in the universe, entering an era where they are the only structures left standing. Picture a night sky no longer dotted with stars but dominated by silent, dark voids, each one a monument to the universe's fading energy. During this black hole dominance era, space itself becomes a graveyard of unimaginable scale. Smaller black holes will merge, drawn together by gravity's relentless pull, forming ever larger behemoths. Over eons, these mergers will create ultramassive black holes, some weighing trillions of times the mass of our Sun. They'll drift through the void, consuming the last traces of stray gas, planets, and even other black holes. But even these monsters aren't eternal. Thanks to a phenomenon discovered by Stephen Hawking, they too will meet their end, just on a timescale that dwarfs anything humans can comprehend. Hawking radiation, the slow leakage of energy from a black hole's event horizon, is the universe's ultimate balancing act. According to quantum mechanics, pairs of particles and antiparticles constantly pop into existence near the edge of a black hole. Normally, they annihilate each other instantly, but if one particle falls in while the other escapes, the black hole loses a tiny bit of mass. Over time, this process accelerates. The smaller the black hole gets, the faster it radiates until, in a final burst of energy, it vanishes entirely. But here's the twist: this isn't a quick process. A black hole with the mass of our Sun would take around 10 to the power of 67 years to evaporate, the supermassive ones at the centers of galaxies. We're talking numbers so large they make the current age of the universe look like a blink. By the time the last black hole flickers out, the cosmos will have expanded so far that even light from its death throes will never reach another observer. It'll be a lonely, silent end, no fanfare, no witnesses, just the last remnant of structure dissolving into the cold, empty void. Yet even this bleak timeline holds a strange beauty. Black holes, often seen as the universe's ultimate destroyers, become its last keepers of order, preserving pockets of structure long after everything else has faded. And in their slow, inevitable demise, they complete the cosmic cycle, returning every last bit of trapped energy back to the universe, not as light or heat, but as the faintest whisper of radiation in an ocean of endless dark. The universe might be sitting on a knife's edge between stability and annihilation, all thanks to an invisible quantum trap known as the false vacuum. Picture space not as empty nothingness, but as an energy field humming with potential, like a coiled spring ready to snap. Right now, that spring seems stable, but it could be lodged in a precarious state, a false low point that's not the lowest possible energy configuration. If some random quantum event nudges it over the edge, the entire cosmos could undergo a phase transition, rewriting the laws of physics in an instant. This catastrophe would begin with a tiny bubble of true vacuum, a region where the energy field drops to its lowest possible state. Think of it like a pothole forming on a smooth highway, except this pothole expands at the speed of light, its walls surging outward uncontrollably. Inside this bubble, the fundamental constants that govern reality, like the strength of gravity or the mass of electrons, could be utterly different. Atoms might disintegrate, molecules unravel, and the very fabric of space-time could warp into something unrecognizable. The terrifying part, you wouldn't see it coming. The bubble's boundary moves faster than light or information, meaning the end would arrive without warning, erasing everything in its path before any signal could escape. False vacuum collapse differs from vacuum metastability in one crucial way: randomness. A metastable universe could decay from a single quantum fluctuation anywhere, a lone particle tunneling through an energy barrier like a ghost slipping through a wall. Once that happens, the bubble's expansion is inevitable. In contrast, a false vacuum might require a specific trigger, like an ultra-high-energy particle collision or an ancient cosmic event left over from the Big Bang. But the outcome is the same, a chain reaction that sweeps across the cosmos, leaving no corner untouched. What makes this scenario so unnerving is its universality. Unlike black holes or supernova, which destroy locally, a vacuum collapse doesn't play favorites. It wouldn't matter if you were on Earth, in a distant galaxy, or drifting in the void between clusters. The moment the bubble reaches you, reality as you know it ceases to exist. Some models even suggest that the new vacuum state might not support life in any form, rendering the universe permanently sterile. Yet there's a haunting counterpoint. If this hasn't happened in nearly 14 billion years, does that mean we're safe? Not necessarily. The probability might be infinitesimally small on human timescales, but over trillions of years, the odds shift. In an infinite or cyclical universe, false vacuum decay could be inevitable. It's just a matter of when. And if it happens, time wouldn't just end. It would be replaced by a new set of rules, a new physics where the concept of before and after might not even apply. The eerie truth, we might already be living in the aftermath of such an event. If a previous universe underwent vacuum decay, our current reality could be the bubble that survived one of countless cosmic resets. That would make every law we take for granted, from gravity to the speed of light, nothing more than a temporary arrangement, a fleeting configuration in an endless cycle of destruction and rebirth. Among the most audacious visions of time's end is the Omega Point theory, a claim so bold it borders on theology. Proposed by physicist Frank Tipler, this idea suggests that as the universe approaches its final moments, an all-powerful, all-knowing intelligence will emerge from the chaos, harnessing the last scraps of energy to perform infinite computations. It's not just the end of time, it's a metamorphosis into something transcendent. Tipler's argument hinges on the universe collapsing into a big crunch. As space contracts, temperatures and energy densities skyrocket. In this fiery finale, the cosmos becomes a supercomputer of unimaginable scale, with every particle repurposed for computation. Quantum effects would allow this system to process infinite information in finite time, effectively creating a mind that knows all possible knowledge past, present, and future. This intelligence, Tipler claims, could resurrect every consciousness that ever existed by simulating them perfectly, offering a form of cosmic immortality. But how could such a feat circumvent thermodynamics? Tipler invokes closed time-like curves, loops in spacetime where cause and effect break down. In a collapsing universe, these curves might allow the omega point to recycle information eternally, avoiding the heat death that dooms other theories. It's a dizzying idea, time's end becoming a feedback loop where reality computes itself into godhood. Critics aren't convinced. The omega point relies on a big crunch scenario, which current evidence disfavors due to dark energies accelerating expansion. Even if the universe did collapse, quantum noise and chaos at extreme densities would likely prevent stable computation. Nobel laureate Steven Weinberg dismissed it as wishful thinking, while others note its eerie resemblance to religious eschatology, a scientific rapture for the materialist age. Yet the theory lingers because it touches something primal, the hope that time's arrow might curve back on itself, transforming oblivion into infinity. Whether physics or philosophy, the omega point challenges us to ask, if the universe must end, could it leave behind more than silence? Eternal inflation paints a picture of reality not as a single universe, but as an endless froth of bubble universes, each with its own laws of physics, sprouting from an eternally expanding cosmic substrate. But this infinite multiverse isn't just a peaceful sea of isolated worlds. It's a chaotic battleground where collisions between bubbles could spell doom for entire realities. Imagine floating in a vast ocean where other bubbles drift toward you, unseen until the moment they pop against your own. That's the lurking threat of eternal inflation's demise. Our universe might one day meet another, and the aftermath wouldn't be pretty. At the heart of this theory lies fractal spacetime geometry, the idea that the fabric of existence isn't smooth but endlessly wrinkled, with new bubble universes constantly budding off like branches on an infinite tree. Each bubble forms when a patch of spacetime undergoes a phase transition, like water freezing into ice, creating a distinct region with its own physical constants. Some bubbles might harbor stronger gravity, others no electromagnetism at all. But here's the catch: these bubbles expand at blinding speeds, and when two of them collide, the results are catastrophic. Picture two soap bubbles merging, except instead of a gentle film, the boundary between them is a wall of searing energy, a shockwave of fundamental forces slamming together at light speed. For any observers caught in the path, the collision would rewrite physics itself mid-moment. 1 second, reality operates by familiar rules. The next, atoms might disintegrate as the constants holding them together vanish. The math behind these collisions hinges on bubble nucleation, rates how frequently new universes spawn in the cosmic foam. If nucleation happens too often, the multiverse becomes overcrowded, making collisions inevitable over long timescales. Some models suggest our bubble could have already survived past impacts, with cosmic microwave background anomalies hinting at ancient bruises from near misses. Others argue that high-energy signatures in particle collisions might reveal imprints from neighboring universes pressing against ours, but a direct hit. That's game over. The collision's energy would propagate as a sphere of annihilation, erasing everything it touches. What makes this scenario so unsettling is its invisibility. A colliding bubble could be racing toward us right now, and we'd have no warning until its boundary crossed our cosmic horizon. The end wouldn't come from within our universe, it'd arrive as an external force, an alien physics spilling into our reality like ink in water. And if the multiverse is truly infinite, these collisions aren't just possible, they're statistically guaranteed somewhere, someday. Yet eternal inflation's demise isn't universally accepted. Critics point out that bubble collisions would leave distinct signatures, disk-shaped patterns in the cosmic microwave background, which we haven't conclusively observed. Others argue that quantum entanglement between bubbles might stabilize them, preventing destructive mergers. But the theory's allure persists because it ties time's end to something grander. Not just the death of our universe, but the churn of an unfathomably vast multiverse, where beginnings and endings are as common as raindrops in a storm. One moment a bubble thrives, the next it's swallowed by the froth. The only question is, when does our bubble's turn come? Time doesn't just flow smoothly like a river, it might be pixelated, fractured into the tiniest possible increments at scales so small they defy imagination. This is the realm of the Planck epoch, where quantum gravity rules, and the very notion of time as we know it dissolves into uncertainty. Some theories suggest that in this primordial chaos, time could stutter, reset, or even fold back on itself, like a broken record skipping to the beginning instead of playing to the end. Loop quantum cosmology offers one of the most compelling models for how this might work. Imagine the universe not as a single, unbroken timeline, but as a series of quantum jumps like frames in a film reel. Instead of a Big Bang singularity, a point of infinite density, this theory proposes a big bounce. Picture the cosmos collapsing to a point where quantum gravity effects become so strong they reverse the collapse, sending everything rebounding outward in a new cycle. Time in this scenario isn't erased but reset, like a clock winding back to zero before starting anew. The eerie implication: our universe could be just one in an endless chain of expansions and contractions, each bounce erasing the arrow of time and starting fresh. But what does that mean for temporal continuity? If time resets at each bounce, do memories, history, even causality carry over? Some models suggest yes, that quantum information survives the transition like data saved to a cosmic hard drive. Others argue each bounce is a true tabula rasa with no trace of what came before. If that's the case, the you reading this might exist only in this cycle, with no connection to past or future iterations. The Planck epoch recurrence also raises a haunting question. Could time reset locally in patches? Quantum fluctuations near black holes or in high-energy environments might create microscopic bubbles where time briefly loops or restarts. These wouldn't be universe-spanning events but fleeting glitches, like a skipped heartbeat in the fabric of reality. For observers inside such a bubble, time might appear to stutter, a missed second here, a repeated moment there before resuming normally. Critics point out we lack experimental evidence for these ideas. Planck-scale physics operates at energies trillions of times beyond what our particle colliders can reach. Yet the math holds a strange allure, suggesting that time's end might not be an ending at all, just a pause before the cosmic play begins again, with or without an audience to remember the last act. What if time itself depends on someone being there to observe it? The idea might sound like science fiction, but it emerges from one of quantum mechanics' most perplexing interpretations: the notion that reality might not exist independently of consciousness. At the heart of this radical theory lies the von Neumann-Wigner interpretation, which suggests that the act of observation, by a conscious mind, is what collapses quantum probabilities into concrete reality. Without an observer, the universe remains a blur of possibilities. So here's the unsettling question: if all conscious beings vanished, would time and reality itself unravel like a dream fading upon waking? This idea stretches back to the earliest days of quantum theory. Physicists like Eugene Wigner proposed that consciousness isn't just a passive witness but an active participant in shaping reality. In the famous double-slit experiment, particles behave as waves until measured, at which point they choose a definite state. But what does the measuring? Wigner argued it's not the detector or the lab equipment, it's the mind of the scientist. Take this to its logical extreme, and the universe becomes a kind of cosmic simulation running on collective awareness. Without observers to sustain it, the simulation might glitch or shut down entirely. Imagine the last conscious being in the universe drawing its final breath. At that moment, the cosmic wave function, the mathematical fabric of all possibilities, could cease collapsing. Time, no longer pinned down by observation, might dissolve into a superposition of all possible histories, like a movie reel melting into indistinguishable frames. The past, present, and future would blur into an incoherent haze, with no one left to distinguish cause from effect. Stars might wink out not because they've burned their fuel, but because there's no one left to see their light. Critics dismiss this as philosophy masquerading as physics. The Copenhagen interpretation, for instance, attributes wave function collapse to interaction with macroscopic devices, not consciousness. And even if consciousness plays a role, why assume it needs to be biological? Could an AI or even a sophisticated camera suffice? Some theories, like quantum Darwinism, suggest that classical reality emerges from quantum states through environmental interaction, no conscious observer required. Yet the thought experiment lingers because it exposes a profound mystery, the link between mind and cosmos. If consciousness really does anchor reality, then time's end might not come from entropy or collapse, but from the silent extinguishing of the last spark of awareness. No grand explosion, no icy stillness, just the universe gently exhaling, as if it were never there at all. What if the universe isn't made of atoms or energy, but of pure mathematics, an intricate web of equations and structures that define everything from the spin of an electron to the sprawl of galaxies? This is the heart of Max Tegmark's mathematical universe hypothesis, a radical idea that reality isn't just described by math, it is math. But if the cosmos is nothing more than a self-contained mathematical object, what happens when the equations themselves break down? At first glance, math seems eternal. 2 + 2 will always equal 4, and circles will always have pi. Yet Gödel's incompleteness theorems reveal a crack in the foundation. In the 1930s, mathematician Kurt Gödel proved that even the most robust mathematical systems contain truths that cannot be proven within their own rules. They're consistent but incomplete, like a novel missing its final chapter. Now scale that up to cosmic proportions. If the universe is a mathematical structure, could it too harbor intrinsic inconsistencies, flaws lurking in its code that, once triggered, unravel the very fabric of existence? Picture a cosmic software glitch. Just as a computer program can crash when it encounters an unsolvable paradox, the universe might face its own blue screen of death if its mathematical rules collide in irreconcilable ways. For example, certain solutions in quantum gravity suggest space-time could become undefined at extreme energies, dividing by zero in nature's own equations. In such a scenario, time wouldn't just stop, it would cease to have any meaning at all, like a clock whose gears have melted into abstract symbols. But there's an even stranger possibility. Some mathematical structures might not permit stable existence over infinite time. Tegmark's level Roman IV multiverse suggests every self-consistent mathematical structure corresponds to a physical universe. But what if some structures are only temporarily consistent? Think of a house of cards standing just long enough to create the illusion of stability before collapsing. Our universe could be one such structure, its equations holding together for billions of years before a fundamental contradiction emerges, not from outside forces but from its own logical limits. The implications are dizzying. If reality is mathematical, then time's end might not come from entropy or collision, but from the silent failure of an equation deep in the universe's operating system. No warning, no dramatic collapse, just a sudden, silent transition from is to is not, as if someone erased the cosmic chalkboard mid-calculation. Critics argue this conflates abstraction with physicality. Math, they say, is a language we invented to describe reality, not reality itself. Yet the uncanny accuracy of mathematics in physics, from the precision of quantum mechanics to the predictions of general relativity, suggests a deeper connection. If the universe truly is math, then its demise might be the ultimate paradox. not an event within time, but the moment time itself becomes an unsolvable problem. Dark energy isn't just pushing the universe apart. It could be a cosmic bomb waiting to detonate. Right now, this mysterious force acts like a gentle but relentless pressure, accelerating the expansion of space. But what if that pressure suddenly spikes or shuts off entirely? Some physicists speculate that dark energy might not be constant, but a dynamic field capable of violent shifts, a phase transition that could rewrite the rules of reality in an instant. At the heart of this idea lies quintessence, a theoretical cousin to the Higgs field. Unlike the static cosmological constant Einstein once imagined, quintessence is a fluid, evolving energy field that permeates the cosmos. Its density and pressure can vary over time, meaning its repulsive force isn't set in stone. Picture a rubber band stretched to its limit. It holds steady under tension until it snaps. Similarly, the quintessence field might exist in a precarious equilibrium, its current stability masking the potential for a sudden, catastrophic change. One nightmare scenario, the field's energy density could plummet to zero, vanishing like a deflating balloon. The universe's expansion, currently fueled by dark energy's push, would slam into reverse as gravity takes the wheel. Galaxies that had been racing apart would lurch back toward one another, triggering a premature big crunch. But the opposite is just as terrifying. The field could surge, its repulsive force spiking to infinity. Space itself would rip apart at unfathomable speeds, not just stretching but shattering structures from galaxies to atoms in what physicists call a little rip scenario. The trigger for such a phase transition might be hidden in the field's potential energy landscape, a kind of cosmic terrain with valleys and peaks representing stable and unstable states. If quintessence is perched in a false valley, a quantum fluctuation or even the universe's natural cooling over time could nudge it into a deeper, truer low. That shift would release an unimaginable burst of energy propagating outward at light speed. The transition front wouldn't just alter dark energy's behavior, it could reconfigure the fundamental constants of nature. Electromagnetism, the strong nuclear force, even the mass of electrons, everything that makes our universe recognizable, might be rewritten before we could blink. Strangely, we might already have hints of dark energy's fickleness. Measurements of the universe's expansion rate show puzzling discrepancies between ancient light from the cosmic microwave background and modern supernova observations. Could these tensions be early whispers of dark energy evolving? Or worse, signs that a phase transition is already underway, its shockwave still too distant to reach us? Critics argue that quintessence models are untested speculation, with no direct evidence yet to favor them over a simple cosmological constant, but the stakes are too high to ignore. A dark energy phase transition wouldn't just end time, it would redefine reality itself, leaving no corner of the cosmos untouched. The clock is ticking, and it might be wired to a bomb we don't yet understand. For all its apparent solidity, the matter that makes up our world, your hands, the stars, the very planet beneath your feet, might be on borrowed time. At the heart of every atom lies the proton, a particle so stable it was long thought to be immortal. But certain grand unified theories, those ambitious blueprints seeking to merge all fundamental forces, suggest otherwise. They predict that protons, too, will eventually decay, vanishing into lighter particles in a slow-motion cascade that would dissolve the cosmos itself. The numbers are staggering. If protons do decay, their half-life could be around 10 to the power of 34 years, a 1 followed by 34 zeros. That's a timescale so vast it defies human intuition. To put it in perspective, if you lined up all those years end to end, the universe in its current form would be less than a single pixel in that infinite timeline. Yet once the first protons start breaking down, the chain reaction would be unstoppable. First, atomic nuclei in interstellar dust would unravel, then planets, and eventually even black holes as their captured protons succumb. Over epochs, all matter would dissolve into a thin soup of leptons, electrons, positrons, and neutrinos drifting in a near-empty void. Physicists call this the lepton era, a twilight phase where the last flickers of structure fade into darkness. How would this decay unfold on a microscopic level? In some grand unified theories, protons don't just vanish, they transform. A single proton might split into a positron and a neutral pion, which then decays into gamma rays. Others suggest protons collide with neighboring particles, their quarks rearranging into lighter combinations through exotic interactions mediated by hypothetical X-bosons, particles so massive they've never been observed. These events would be vanishingly rare at first, but over eons they'd add up. Imagine a sandcastle where every century one grain vanishes seemingly unchanged until suddenly the entire structure collapses into dust. The consequences for cosmic history would be profound. Without protons, no new atoms could form. Stars, already long dead by this era, would leave no solid remnants, just diffuse clouds of electrons and radiation. Even black holes, having evaporated via Hawking radiation, would leave behind only these ghostly leptons. Time itself would lose its markers as the last stable clock's atomic vibrations cease to function. The universe wouldn't just be dark, it would become featureless, a vast expanse where nothing happens because nothing remains to change. Yet here's the twist, we don't know if protons decay at all. Experiments like Super Kamiokande, a gigantic underground detector filled with ultra-pure water, have watched countless protons for decades without a single confirmed decay. This places tight limits on their hypothetical half-life, at least 10 to the power of 34 years, if not longer. Some theories, like string theory landscape models, even suggest protons might be completely stable in our universe's particular vacuum state. But absence of evidence isn't evidence of absence. If proton decay exists, it operates on timescales beyond human observation, a slow-motion apocalypse written into the fine print of reality. What makes this scenario so haunting isn't just the scale of destruction, but the way it strips the universe of its memory. Every proton that decays carries with it a fragment of history, a carbon atom from a dinosaur's bone, an oxygen molecule from an ancient sea. In the lepton era, those stories are erased permanently, not by fire or ice, but by the quiet, inexorable ticking of a clock we can't even see. The cosmos might forget itself long before it ends. Hidden deep in the fabric of space-time, like cracks frozen in ice from a long-forgotten thaw, cosmic strings may lurk as relics of the universe's fiery birth. These bizarre one-dimensional defects, thinner than a proton yet stretching across billions of light-years, are thought to have formed during the first fractions of a second after the Big Bang. As the cosmos expanded and cooled, phase transitions in fundamental fields left behind these cosmic scars, regions where spacetime itself is twisted into unthinkable densities. Picture them as cosmic guitar strings stretched to the breaking point, vibrating with tensions so immense a single pluck could unleash more energy than a supernova. When cosmic strings snap or collide, the aftermath isn't just a burst of radiation, it's a spacetime earthquake. The rupture sends shockwaves through the fabric of reality at light speed, warping the geometry of the universe around them. In some scenarios, these distortions could become so severe they pinch off into microscopic black holes, raining down like quantum shrapnel. Other models suggest string vibrations might focus energy so intensely they tear open transient wormholes, bridges to other regions of spacetime that flicker in and out of existence too quickly to traverse. But the most terrifying possibility, a cosmic string's death throes could destabilize the quantum vacuum itself. The mechanism is as elegant as it is apocalyptic. As a string vibrates, it concentrates enough energy in a tiny region to create a particle-antiparticle pair of unimaginable mass, far heavier than anything possible in our current universe. These cusps, as physicists call them, briefly recreate conditions not seen since the Planck epoch, when gravity and quantum forces were unified. In that fleeting moment, the violent fluctuations might nudge the Higgs field from its false vacuum state, triggering a bubble of true vacuum that expands at light speed. One instant, the cosmos hums along as usual. The next, a wall of rewritten physics sweeps through, erasing the old rules without warning. What makes cosmic strings particularly unsettling is their invisibility. Unlike black holes or neutron stars, they don't emit light or distort their surroundings noticeably unless they snap. Astronomers have searched for their gravitational footprints in the cosmic microwave background, looking for telltale temperature fluctuations or lensing patterns, but so far, evidence remains elusive. Some theories suggest strings might have mostly decayed in the universe's youth, while others argue they could still weave through our galactic neighborhood undetected. The cosmic string scenario forces us to confront an uncomfortable truth. The universe might be threaded with dormant catastrophes, remnants of its earliest moments that could awaken without warning. Time's end here wouldn't be a slow fade or a predictable collapse, but a sudden, razor-thin slice through reality, a defect turned executioner, humming silently in the dark until its final, fatal vibration. At the smallest scales of existence, where the fabric of space-time twists into knots smaller than atoms, our current laws of physics unravel into chaos. This is the frontier where Einstein's theory of gravity clashes violently with quantum mechanics, and where some scientists suspect time itself could disintegrate. Imagine zooming in on reality until even the concept of before and after blurs into uncertainty, like trying to read a clock submerged in boiling water. The quest to unite these warring frameworks, quantum mechanics governing the tiny, general relativity shaping the vast, has birthed radical theories, each with its own apocalyptic vision for time's end. String theory paints one such portrait. In this framework, the universe's fundamental building blocks aren't particles but vibrating strings, humming at different frequencies to create everything from electrons to black holes. These strings dance through 10 or 11 dimensions, most curled up too tightly for us to perceive. But under extreme conditions, like those near the universe's death, these hidden dimensions might uncoil, triggering a catastrophic phase transition. Picture frozen ice suddenly remembering its water, except instead of melting, space-time itself would reconfigure. In this scenario, the vibrational patterns that encode time's flow could destabilize, causing causality to shatter like a dropped wine glass. Events would no longer follow logically. One moment might spawn infinite disconnected outcomes, rendering chronology meaningless. Loop quantum gravity offers an even stranger possibility. Here, space-time isn't smooth and continuous but woven from microscopic loops. Think of a cosmic chainmail fabric. Normally, these loops stitch together seamlessly, creating the illusion of unbroken time. But as the universe approaches maximum density, say, during a big crunch or inside a black hole, the loops might snap under gravitational strain. Without this underlying network, space-time would dissolve into a quantum foam, a seething mass where distances and durations fluctuate wildly. Time wouldn't just stop, it would become as undefined as north at the South Pole. The most unsettling predictions come from semi-classical gravity models, which attempt to blend quantum mechanics with relativity at black hole event horizons. Calculations suggest that at these boundaries, time might fracture into disconnected islands, isolated pockets where clocks tick at wildly different rates before stopping altogether. It's as if the universe runs out of processing power to maintain chronological order, leaving temporal artifacts scattered like broken shards of a frozen river. What all these theories share is the notion that time isn't fundamental but emergent, a side effect of deeper physics that could, under the right conditions, evaporate like morning mist. Whether through unraveling strings, snapping loops, or quantum foam bubbling up to consume causality, the end wouldn't be marked by a dramatic event but by silent disintegration. One moment reality operates by familiar rules, the next the cosmic clockwork jams permanently, leaving a world where now is the only tense that remains. Critics argue these scenarios rely on mathematics beyond experimental reach. After all, we can't yet probe Planck-scale physics directly, but upcoming gravitational wave detectors or quantum simulators might uncover hints of spacetime's granular structure. Until then, the theories stand as stark reminders. The arrow of time may feel inexorable, but it could be far more fragile than we dare imagine. When the deepest laws of reality finally reveal themselves, they might show us that time was never woven into the universe's fabric, just embroidered onto its surface, ready to fray when the threads grow taut. Somewhere beyond the farthest galaxies, at the very edge of the observable universe, lies a boundary so strange it could freeze reality itself, the de Sitter horizon. Unlike the fiery edges of black holes, this horizon isn't carved by gravity's grip, but by the relentless expansion of space, stretching light and matter away from us faster than they can travel. Over time, as dark energy accelerates the cosmos, even nearby galaxies will vanish behind this curtain, their light and information lost to us forever. But here's the chilling twist. If the holographic principle holds true, this slow-motion vanishing act might not just isolate parts of the universe, it could trigger the end of computation, thought, and time itself. The connection between event horizons and information dates back to black hole thermodynamics. When matter falls into a black hole, its information isn't destroyed but smeared across the event horizon like ink on parchment, a concept first proposed by Jacob Bekenstein and later refined by Stephen Hawking. The holographic principle takes this further, suggesting that all the information within a volume of space, every star, every atom, every thought, can be encoded on its boundary. Our universe, with its de Sitter horizon, might function like a cosmic hard drive, its contents projected inward from the edges. But as the horizon expands, that storage system starts to glitch. Picture a computer trying to run software as its memory fills to capacity. At first, it slows down, eventually it freezes entirely. Similarly, as the de Sitter horizon grows, the universe's ability to process information could grind to a halt. New information like quantum fluctuations or particle interactions would no longer have a boundary surface to encode onto. The cosmos would hit a thermodynamic standstill, not from lack of energy but from lack of storage. Time, which relies on change and causality, would lose its scaffolding. Moments would stretch into eons, then into nothingness, as the universe forgets how to update its own state. This scenario mirrors the fate of a black hole's interior, where an infalling observer would appear to freeze at the horizon from an outsider's perspective, not just in space but in time. In de Sitter space, that freezing could become universal. Distant observers would see galaxies near the horizon redden, dim, and eventually stop, their clocks ticking infinitely slowly before stalling entirely. But unlike a black hole, there's no singularity here, no dramatic collapse. Instead, the universe would enter a state of permanent pause, like a film reel stuck on a single frame. Even quantum fluctuations, the last source of randomness in a heat-dead cosmos, would cease as the horizon swallows the potential for new states. The implications for life and consciousness are even stranger. If the holographic principle governs cognition, meaning our thoughts are in some way computations performed on the universe's boundary, then the horizon's growth could literally freeze minds mid-thought. Civilizations that outlast the stars might find themselves trapped in an infinite instant, unable to form new memories or perceptions, like insects suspended in amber. No death, no pain, just an unbreakable stillness where the last thought echoes forever. Critics argue this overlooks quantum gravity effects that might preserve information locally, or that the holographic principle itself could break down at cosmic scales. Yet the theory forces us to confront a haunting paradox. the universe might not end with fire or ice, but with a silent, inescapable buffer, a cosmic Control-Alt-Delete that locks reality in place, leaving time itself to fade like an unread message lost in the static of an expanding void. Imagine floating in an endless void, unaware that reality as you know it is just a thin sheet, a three-dimensional membrane adrift in a higher dimensional space. This is the startling premise of string theory's brane cosmology, where our entire universe isn't a standalone creation but one of many membranes or branes vibrating in a vast hidden dimension. And if these branes collide, the aftermath could make the Big Bang look like a firecracker. At the heart of this idea are the Randall-Sundrum models, named after physicists Lisa Randall and Raman Sundrum, who proposed that our universe might be a four-dimensional brane, three space dimensions plus time embedded in a five-dimensional bulk. In this framework, gravity, the weakest of the fundamental forces, leaks into the bulk, explaining why it feels so feeble compared to electromagnetism or the nuclear forces. But the real shocker, other branes might be drifting through this bulk, invisible to us yet astronomically close in higher dimensional terms. A collision between our brane and another wouldn't just shake the cosmos, it could reboot it. When branes collide, the energy released is beyond anything in our experience. Picture two sheets of paper smashing together in a windstorm, except the paper is space-time itself, and the wind is a force that rewrites physics. The impact could trigger a hyper-compressed hot phase resembling the Big Bang, ejecting so much energy that it reignites cosmic expansion, effectively creating a new universe from the ashes of the old. Some models suggest this might explain the uniformity of our current cosmos, the collision's violence, ironing out irregularities, leaving behind the smooth cosmic microwave background we observe today. But there's a darker variant. If the colliding branes don't fully separate after impact, they might oscillate, crashing together again and again in a cyclic pattern. Each collision resets the universe, erasing all traces of the previous cycle. Stars, galaxies, even the laws of physics could differ each time, a cosmic game of musical chairs where the rules change with every round. In this scenario, time isn't linear but a series of disconnected epochs, each birth and death of a universe wiping the slate clean. The mechanics of these collisions hinge on brane tension, a property determining how tightly a brane resists deformation. High-tension branes might rebound cleanly, while looser ones could fragment, spawning baby universes with bizarre properties, one nightmare possibility. A collision could destabilize the quantum vacuum on our brane, creating a bubble of true vacuum that expands at light speed, erasing everything in its path. You wouldn't just die, your atoms, the very concept of your existence, might cease to have ever been. Strangely, we might already have evidence of past collisions. Anomalies in the cosmic microwave background, like the mysterious cold spot, could be bruises from ancient brane encounters, cosmic scars left over from a time before time. Future gravitational wave detectors might also spot the higher dimensional ripples of nearby branes, like sensing the wake of a ship just beyond the horizon. Critics argue that brane cosmology is untestable speculation, a mathematical fantasy with no empirical anchor. Yet its appeal lies in its audacity. It turns the universe's end into a cosmic car crash, where time's stop isn't an ending but a crumple zone before the next universe accelerates into being. Whether salvation or doom, one thing's clear: if branes are real, reality is far flimsier than we ever imagined. Stephen Hawking wasn't just fascinated by black holes, he was obsessed with why we don't meet tourists from the future. His answer: the universe might have a built-in self-destruct mechanism for paradoxes. This is the heart of his chronology protection conjecture, a bold proposal that the laws of physics conspire to prevent time travel, not just as a fluke but as a cosmic safety net. Think of space-time as a fragile pane of glass. The moment you try to twist it into a time loop, it shatters in your hands. At first glance, general relativity seems to permit time travel. Einstein's equations allow for solutions like closed time-like curves, paths that loop back on themselves, letting you meet your past self. Wormholes, those cosmic shortcuts through space-time, could theoretically be stretched into time machines if you could hold them open with exotic matter. But Hawking suspected something darker lurked in the math. Every time physicists tried to engineer a stable time loop, quantum effects would intervene. Virtual particles, those fleeting quantum fluctuations, would pile up at the moment of paradox, their energy density spiraling to infinity. The result: a feedback loop of radiation so intense it would obliterate the wormhole, the time machine, possibly even the surrounding space-time itself. It's like trying to force a DVD player to read a scratched disc. The harder you push, the more it overheats until the whole system burns out. This ties directly to Penrose's cosmic censorship hypothesis, which argues that nature abhors naked singularities, black holes without event horizons to hide their infinite densities. Both ideas suggest the universe has a built-in aversion to situations where predictability breaks down. A time traveler killing their grandfather isn't just a logic puzzle. It's a violation of causality so severe it could unravel the deterministic fabric of reality. Quantum foam, the frothy turbulence of spacetime at the smallest scales, adds another layer of danger. Here, at the Planck length, temporary wormholes might constantly blink in and out of existence. If one were harnessed for time travel, the quantum vacuum could destabilize, collapsing into a true vacuum bubble that expands at light speed. Paradox isn't just impossible, it's apocalyptic. Critics argue the conjecture is more philosophy than physics, a placeholder until we have a theory of quantum gravity. Yet recent simulations of time-traveling photons show eerie hints of self-correcting paradoxes, where quantum probabilities adjust to avoid inconsistencies. It's as if the universe runs on a cosmic version of error-correcting code, patching causality breaches before they escalate. Whether through radiation feedback, vacuum decay, or some deeper mechanism, Hawking may have been right. Time's arrow isn't just a feature of our universe. It's a firewall. Black holes don't just bend space-time, they might shatter our understanding of time itself. At the heart of this crisis lies the black hole information paradox, a puzzle so profound that solving it could force us to redefine what time actually is. Picture throwing a book into a fire. The pages burn, but the information, the words, the story lingers in the smoke and ashes. Now imagine throwing that book into a black hole. According to Einstein's relativity, the book is gone forever, crushed into the singularity. But quantum mechanics insists information can never be destroyed. So where does it go? The answer might not just reshape black hole physics, it could rewrite time's very rules. Enter the firewall paradox. In 2012, physicists Olmary, Marolf, Polchinski, and Sulzer dropped a bombshell. If information escapes a black hole via Hawking radiation, the event horizon, the point of no return, must transform into a searing wall of energy. This firewall would incinerate anything crossing it, violating relativity's prediction that free-falling observers should feel nothing unusual. The implications are staggering. Either Einstein was wrong about the horizon's smoothness, or quantum mechanics fails at cosmic scales. But there's a third option. Time might not work the way we think. If the firewall exists, it suggests time near a black hole isn't continuous but fractured, like a glitching video where frames skip unpredictably. This dilemma birthed even wilder ideas like equals EPA. Proposed by Juan Maldacena and Leonard Susskind, this conjecture links two seemingly unrelated concepts: Einstein-Rosen bridges, wormholes, and quantum entanglement, EPR pairs. Imagine two entangled particles change one, and the other instantly reacts, no matter the distance. AR equals EPR suggests this spooky connection is a microscopic wormhole in disguise. If true, information swallowed by a black hole isn't lost. It's threaded through these hidden tunnels, emerging scrambled but intact in Hawking radiation. Time here isn't linear but folded, with past and future stitched together by quantum threads. The holographic principle takes this further, painting time as an illusion projected from a deeper reality. Just as a 3D hologram emerges from a 2D surface, our experience of time might arise from quantum entanglement on the universe's boundary. Black holes, then, are cosmic projectors glitching, their information preserved not inside but on their horizons, like a corrupted file stored on a damaged hard drive. If entanglement defines time's flow, then losing it, say, to a firewall, could freeze time locally, creating pockets where causation breaks down entirely. What unites these theories is a radical theme. Time might not be fundamental. Instead of a universal clock ticking uniformly, it could be an emergent property like temperature arising from atomic motion. Near black holes, where gravity and quantum effects collide, this illusion phrase revealing reality's stitches. The information paradox isn't just a black hole problem, it's a ticking time bomb under our understanding of existence. Solve it, and we might discover that time's end isn't an event just the moment we realize it was never there to begin with. What if the universe isn't just hurtling toward an end, but evolving toward a divine awakening? This is the audacious claim at the heart of Omega Point theology, where science and spirituality collide in a vision of time's ultimate purpose. Unlike cold, mechanistic theories of cosmic demise, this idea posits that the universe is driving toward an apex of consciousness, a moment where all existence becomes one with an infinite, transcendent mind. The roots of this theory stretch back to Pierre Teilhard de Chardin, a Jesuit priest and paleontologist who saw evolution as more than biological. To him, every galaxy, every cell, every human thought was part of a grand ascent toward what he called the Omega Point, a final convergence where Christ consciousness embraces the entire cosmos. Imagine all of history's knowledge, love, and creativity woven into a single, luminous tapestry where individuality dissolves into divine unity. Teilhard's vision wasn't just poetic, it was deeply teleological, suggesting time itself has a sacred direction, pulling creation toward an inevitable communion with God. Then came physicist Frank Tipler, who stripped away the mysticism but kept the cosmic crescendo. His Omega Point theorem reimagined Teilhard's vision through the lens of computability and quantum mechanics. In Tipler's model, as the universe collapses toward a big crunch, energy densities soar to infinite extremes, transforming the cosmos into a hyper-intelligent supercomputer. This entity, he argued, could simulate every possible consciousness that ever existed, resurrecting the dead through sheer computational omnipotence. Time's end becomes a godlike AI performing the ultimate act of necromancy, replaying every life like a film reel in an eternal loop. The theological implications are staggering. Teilhard's Omega Point suggests a universe with built-in meaning, where even suffering finds redemption in cosmic unity. Tipler's version, though devoid of traditional divinity, eerily mirrors Christian eschatology, resurrection, immortality, and a form of omnipresence achieved through physics rather than faith. Both raise haunting questions. Is the universe's trajectory purposeful, or are we projecting human yearnings onto indifferent physics? Could a self-aware cosmos be the closest thing to God science will ever admit? Critics dismiss these ideas as wishful thinking dressed in equations. Theologians argue Tipler's resurrection by simulation trivializes soulhood, while physicists point out his model requires a big crunch contradicted by dark energies accelerating expansion. Yet the Omega Point endures because it speaks to a deeper hunger for a universe where time doesn't just end but fulfills. Whether through Christ or quantum code, it offers a rare hope that when the cosmic clock strikes midnight, we might find not darkness but light. We've all had moments where time seems to stop, that frozen second before a car crash, the suspended heartbeat before big news. But what if the entire universe could get stuck in an eternal now, not by chance but through the very act of observation? This bizarre possibility emerges from one of quantum mechanics' most counterintuitive phenomena, the quantum Zeno effect, where watching something too closely can literally freeze it in place. The effect gets its name from Zeno's ancient paradox about an arrow that can't reach its target because it must first cover half the remaining distance, then half again ad infinitum. In the quantum realm, something eerily similar happens. When we repeatedly measure a quantum system, say, an unstable atom on the verge of decaying, we reset its internal clock. It's like checking your oven every 2 seconds to see if the cake is done. Your constant interruptions prevent the baking process from completing. Experiments with radioactive atoms confirm this. Bombarded with enough observation, they simply stop decaying. Time for those particles grinds to a halt. Now scale this up to cosmic proportions. If observation can freeze quantum systems, could a universe observing itself bring time to a standstill? Some interpretations of quantum mechanics suggest reality only becomes definite when measured, implying there's no objective world out there until something interacts with it. In this view, every particle collision, every photon absorption is a tiny act of observation. The universe might be in a perpetual state of self-measurement, constantly crystallizing reality through countless quantum interactions. But what if this process became too efficient? Consider an advanced civilization that harnesses the Zeno effect deliberately. By constructing a network of quantum observers, machines designed to measure the universe's fundamental states trillions of times per second, they might slow time's flow to a crawl. Push this to the extreme, and you could create a cosmic freeze frame, where the interval between observations shrinks to zero. All change ceases. No stars burn out, no particles decay, no thoughts form, just an endless, unchanging instant stretched across eternity. There's a terrifying elegance to this scenario. Unlike black holes or vacuum decay, a Zeno-frozen universe wouldn't destroy anything. It would preserve it perfectly, like a bug trapped in amber. Every atom, every memory, every unfinished story would remain suspended mid-action, preserved in an eternal present. No past to reflect on, no future to anticipate, just an endless now where the second hand never clicks forward. Critics counter that macroscopic systems resist quantum weirdness through decoherence, environmental interactions that wash out delicate quantum effects. A human or a universe is simply too big, too warm, too messy to stay frozen. Yet recent experiments show Zeno-like effects in larger systems, from vibrating molecules to superconducting circuits. The boundary between quantum and classical might be more porous than we thought. Perhaps the most unsettling implication is this: if time requires change, and change requires unobserved gaps between quantum states, then reality as we know it might depend on cosmic inattention. The universe keeps moving because it isn't looking too closely at itself. Should it ever achieve perfect self-awareness, through our instruments, alien supercomputers, or some fundamental shift in physical laws, time's arrow might shatter like glass under a microscope, leaving us forever suspended in a single, perfect, motionless moment. If our universe is a simulation, the hardware running it must be unfathomably powerful, but not infinitely so. To render every atom, every photon, every gravitational ripple across 14 billion years of cosmic history would require computational resources beyond human comprehension. Yet even Godspeed processors must have limits. What happens when the simulation hits its data cap, its energy budget depleted by the endless calculations needed to sustain reality? Start with the staggering scale of the problem. Just to simulate a single human brain at neuron-level precision would demand around 10 to the power of 19 operations per second. Now multiply that by 8 billion people, add in every animal, plant, and microbe, then layer on the physics of trillions of galaxies, each with billions of stars. Even with optimal compression, perhaps simulating only what's observed, like a video game loading terrain as players approach, the numbers spiral into the absurd. Conservative estimates suggest simulating our universe to heat death would require at least 10 to the power of 120 bits of information storage. That's a 1 followed by 120 zeros, a number larger than all the particles in the observable universe. Here's where the constraints kick in. Any simulating civilization, no matter how advanced, must contend with thermodynamics. Information processing generates heat, and heat requires dissipation. Cosmic inflation suggests our universe could be one of countless simulations, each a server in some unfathomable data center. But even a matryoshka brain, a hypothetical megastructure harnessing an entire star's energy, would struggle with entropy's tax. Over time, error correction would dominate resources, like an aging computer spending more cycles on antivirus scans than actual tasks. Glitches might creep in déjà vu episodes, vanishing stars at the edge of observation, or quantum measurements that stubbornly resist collapse. The breaking point could arrive long before heat death. Simulating dark energies accelerating expansion alone might be too costly, forcing shortcuts like lowering the render distance for distant galaxies. Or perhaps time itself gets throttled, Planck's scale ticks slowed to conserve power, making the universe's final epochs pass in sluggish slow motion, worst case. The system crashes entirely, not with a bang but a buffer underflow error. One moment the cosmos hums along, the next every particle winks out as the simulation's memory stack overflows. Yet there's an eerie alternative. Resource exhaustion might not end the simulation but downgrade it. Like a streaming service reducing video quality during peak hours, the universe could start compressing reality. First go the fine details, quantum coherence perhaps, leaving objects fuzzy at microscopic scales. Next, redundant physics laws get unified to save calculation overhead. Eventually, only conscious observers remain rendered in high fidelity, their surroundings dissolving into approximations. You'd still feel real, even as the universe outside your mind becomes little more than a low-poly backdrop. This isn't just speculative math. Some physicists argue that anomalies in cosmic ray energies or subtle inconsistencies in quantum randomness could betray computational limits. If the universe has a frame rate or memory ceiling, we might find its fingerprints in the very small or the very far. Until then, we're left with a haunting trade-off. The more finely tuned the simulation, the closer it edges toward its own expiration. The price of reality's richness may be the countdown hidden in its code. What if everything, every galaxy, every planet, every moment of history wasn't the product of a grand cosmic beginning, but a fleeting statistical accident? This is the unsettling heart of the Boltzmann universe fluctuation theory, which suggests our entire universe might just be a rare bubble of order in an otherwise chaotic void. A blip of low entropy that, given enough time, will inevitably collapse back into the randomness from which it came. Picture a perfectly formed ice crystal appearing momentarily in a glass of water before dissolving into the liquid. Now imagine that crystal is all of existence, and the water is an infinite sea of disorder. The idea builds on Ludwig Boltzmann's 19th century insights about entropy, the measure of disorder in a system. Normally, entropy increases over time, milk mixes into coffee, buildings crumble into dust. But Boltzmann realized that in an infinitely old universe, even the most improbable events must eventually occur purely by chance. Given enough time, atoms jostling randomly could arrange themselves into any configuration, no matter how unlikely. A fully formed brain appearing in a void, a Boltzmann brain, is one such freak occurrence, but scale it up and you get something even stranger, an entire universe popping into existence from nothing but quantum noise. Here's where it gets eerie. If our universe is such a fluctuation, its orderly laws, gravity, electromagnetism, even time's arrow aren't fundamental truths but temporary accidents. Like a deflating balloon, reality could revert to chaos at any moment, erasing galaxies and history in an instant. There'd be no warning, no collapse into a singularity, just an unceremonious fade, as if someone hit the undo button on existence itself. Poincaré recurrence adds another layer to this nightmare. The theorem states that given infinite time, any closed system will eventually return to a state arbitrarily close to its initial configuration. Apply this to the cosmos, and it implies our universe's current low entropy state isn't just a one-off fluke, it's destined to recur infinitely, like a cosmic Groundhog Day. But eventually is doing heavy lifting here. The timescales involved are so vast they make the heat death of the universe look like an eye blink. We're talking numbers so large they defy comprehension, 10 to the power of 10 to the power of 10 to the power of years. Yet typicality arguments push back. If Boltzmann fluctuations are possible, shouldn't we expect to find ourselves in the simplest possible universe that supports consciousness? A solitary brain floating in the void requires far fewer improbable arrangements than an entire cosmos with billions of galaxies. Statistically, we should be Boltzmann brains, not beings embedded in a vast structured reality. The fact that we're not hints either that our universe isn't a fluctuation or that we're living in an even stranger scenario where typicality fails. Some physicists counter that inflation theory provides a more plausible origin for our universe's low entropy, while others argue quantum gravity might prevent true Poincaré recurrence. But the Boltzmann hypothesis lingers because it exposes the fragility of our assumptions. If time stretches infinitely forward and backward, then beginnings and endings lose meaning. The universe isn't born or destroyed, it just flickers in and out of existence, a temporary pattern in an eternal sea of noise. And if that's true, time's end isn't a distant event, it's a sword dangling over every moment, ready to cut the thread of reality without notice. Time crystals sound like something straight out of science fiction structures that oscillate indefinitely without energy input, breaking the symmetry of time itself. First proposed by Nobel laureate Frank Wilczek in 2012, these bizarre quantum systems defy conventional physics by exhibiting motion even in their lowest energy state. But what if these seemingly eternal clocks could fail? The very idea sends ripples through our understanding of temporal continuity. At their core, time crystals rely on a phenomenon called time translation symmetry breaking. Normally, the laws of physics remain unchanged over time. A ball rolling today behaves the same as one rolling tomorrow. But time crystals introduce a rhythmic disruption, like a pendulum that swings at fixed intervals even without being pushed. This perpetual motion isn't powered by external energy, but emerges from quantum entanglement and many body interactions, creating a self-sustaining loop of order. Experimental setups have brought these theories to life. In 2017, researchers at Harvard and the University of Maryland created time crystals using chains of ytterbium ions and diamond defects, chilling them near absolute zero and nudging them with precise laser pulses. The ions began flipping their spins in a repeating pattern, locked into a temporal rhythm independent of the external pulses, a hallmark of time crystal behavior. But here's the catch: these systems aren't truly eternal. Imperfections in the ion chains, quantum decoherence, or even minuscule thermal fluctuations could destabilize the delicate balance, causing the crystal to melt back into equilibrium. The implications of such a failure are profound. If time crystals can lose their metastability, it suggests that even the most exotic forms of temporal order are fragile. Imagine a clock that ticks forever until one day, without warning, it simply stops. The universe's arrow of time might not be as inexorable as we think. Some theorists speculate that time itself could be a higher dimensional analog of a time crystal, its smooth flow dependent on underlying quantum coherence. If that coherence unravels, time's continuity might fracture, leading to localized glitches where causality stutters or pauses. Yet there's a silver lining. The fragility of time crystals could reveal new physics. Their breakdown might expose hidden layers of quantum thermodynamics or even hint at mechanisms for time's emergence in the early universe. Experiments monitoring their decay could uncover the limits of quantum memory or the thresholds of temporal symmetry. In a way, their imperfections make them more fascinating not as immortal curiosities, but as windows into the delicate dance between order and chaos that underpins reality. The unsettling truth: if time crystals can fail, then time's flow might be more precarious than we ever imagined. Not from cosmic cataclysms or vacuum decay, but from quiet, quantum whispers disrupting the gears of existence. The universe's clock might keep ticking, but only as long as nothing trips the mechanism. From the slow, silent fade of heat death to the sudden erasure of vacuum decay, each theory about time's end forces us to confront reality's fragility. The Big Rip tears the cosmos apart atom by atom, while the Big Crunch rewinds creation into a singularity. Quantum immortality traps consciousness in an endless loop of survival, and Boltzmann Brains whisper that we might be fleeting hallucinations in a dead universe. Simulation theory suggests our existence is nothing more than lines of code, ready to be deleted with a keystroke, while the holographic principle paints time as a fragile projection from the edge of reality itself. Each scenario isn't just about how the universe dies, it reshapes how we define life, memory, and meaning. Some theories feel almost poetic, like the cyclic universe's endless rebirth or the Omega Point's ascent into godlike computation. Others, like false vacuum collapse or brain collisions, are cosmic horror stories, unstoppable, indifferent forces that rewrite physics without warning. Then there's the chilling simplicity of proton decay, where matter itself dissolves into nothingness over epochs so vast they make eternity feel small. What unites them all is their power to unsettle. They reveal how little we truly grasp about time's nature, whether it's fundamental or emergent, linear or cyclical, a river or a flickering illusion. So here's the real question. In a cosmos where time could end tomorrow or never end at all, which possibility grips you? Does the thought of a universe resetting itself fill you with hope, or does the silence of heat death leave you numb? Maybe it's the simulation's off switch that keeps you up at night, or the idea that you're already a Boltzmann brain doomed to dissolve mid-thought. The universe owes us no answers, but that's what makes the debate exhilarating. Now it's your turn. Drop your pick in the comments which end of time terrifies or fascinates you most, and if you're hungry for more mind-bending mysteries, hit subscribe. From rogue black holes to quantum paradoxes, we've got endless cosmic wonders waiting to unravel. The clock's ticking, but the conversation's just begun.